I took out a lot of the RAID explanation because it was probably a little bit, you needed to really understand RAID and the performance, but I really don't think that for this level course that you want to discuss our architecture all that much. You want to know how to use the realm. But we do need to talk about RAID to understand reconstruction and volume layout and stuff. So we're going to just touch on it. These are the can't get my cursor's trapped. Come on, stop it. There. These are names. This is a view from a client, and we're looking at some directories in a volume. We'll talk about that next. And we see our volume name, the realm name, some subdirectories, some files. Those are all names. This is the name space in the realm. But that's not how the realm operates. The realm operates on objects. Names can change, but the objects and their object IDs never change because we need a permanent way of referring to the same object. Objects are directories, files, and symbolic links. Identifying objects internally by the path of the name is not efficient, so we just want to refer to it by the object ID that look like this. This is the storage manager ID. A storage manager is a service that runs on a director. This is the group ID that corresponds to the volume, and that's something that's unique about this object. The ID for an object never changes. We'll talk about RAID, Bladesets, and volumes. We're doing this so we can get to volumes, but I taught these in another order in another class, and the attendees were not familiar with RAID, and they asked that we talk about RAID first. We do have object-based RAID, and we'll talk about first talk about traditional RAID. RAID originally stood for Redundant Array of Inexpensive Disk, and I put the founders of this seminal article in 1987 down there because Panasas founder Garth Gibson is one of the guys that came up with this. These other people are very prominent as well. The makers of the disk didn't like being called inexpensive, and they were, because at the time, enterprise storage uses very, very expensive SCSI disks because the disks that were on the market that were not SCSI were just not reliable enough. But they were slow and they were expensive. So we came up with RAID, and now the name stands for Redundant Array of Independent Disk to make the manufacturers happy. So by striping data over a number of affordable drives, performance can be increased. Because if you're writing a bunch of data to one drive, you're limited to the spindle speed, where the hard drive's disks are spinning, and the spindle that writes data is seeking, and that can be slow. So instead, we're going to write part of the file to one disk, then I'm going to move to the other, then I'm going to move to the other, and to the other. And there's not that much spindle spin to find the right place on the disk, much, much faster. When we're going to read that file, we're going to read all those parts, but the application needs a single data stream. This is the file. It starts from here to there, and the parts of the file that are put together into the single data stream by a RAID controller. That could be in software, it's usually often in hardware, and that controller can be a huge bottleneck because it has to work very, very hard. Because we're using more disk, the risk of failure increases. And of course, when we change from SCSI to affordable disk, we are also using disks that were not as reliable. To offset this risk, and most hard drives are very reliable these days, but in the early 80s and during the 90s, that was not the case. To offset this risk, most RAID levels include disk redundancy. So if the RAID implementation have a redundancy of 1, that means there is one more disk that is needed to store the data. The redundant disk stores parity information, that is information about all the other data combined, so that if one disk fails, the RAID controller can figure out all the data that was on that disk using the other disk and the parity, and the data can be reconstructed. The number of disk failures that the RAID level can tolerate is equal to its redundancy. RAID controller, if one of the drives fails, RAID controller constructs this missing data to a spare disk. If the spare disk is immediately available to the RAID controller, it is a hot spare. If the RAID implementation has a redundancy of 2, then there are 2 more disks that are needed to store the data. Both redundant disks can store parity data, different data, and it can tolerate 2 failures. In traditional RAID, the data from the entire failed disk is reconstructed onto the spare disk, so this is sometimes called a rebuild. Okay, this is talking about the performance that we're talking about. On these disks, there are units that go kind of horizontally. Those are called stripes. We don't want to calculate parity on the whole disk. We want to have a reasonable chunk. So we're going to calculate that parity per stripe. And the way the parity is written in the arrangement of the stripes is depending on the RAID level. A group of disks in the RAID implementation usually holds many, many different files, and they're all together, and the RAID controller keeps track of where the data for each file is. So let's talk about the RAID levels. RAID 0, redundancy of 0. If any of the disk fails, then the data is gone. This is the highest performing RAID level because no parity is written, but the uses for this are very, very specialized. RAID 1 is not a high performance RAID level. The disk data is mirrored, not striped. So if you have more than one disk, the same data is written to every disk. This is more for safety than anything else. There's no increased RAID performance. The write performance is actually slower because multiple copies are written. This is a data safety. RAID 2, 3, and 4, all these levels have one dedicated data parity disk, and the parity information for each stripe is written to the same disk and is written in a little bit of different ways. And these all have a redundancy of 1. RAID 5, the parity is distributed among the different disks. I'll talk about that later. Some load balancing. Again, the redundancy of 1. The data can be restricted to 1 disk fails, and the parity is usually called P in all these RAID levels. RAID 6, each stripe contains 2 disks with parity information. The parity is distributed as it was, and I'll show you that later. Redundancy is 2, so the data can be reconstructed if 1 or 2 disks fails. And the parity is usually called P. Parities are usually called P and then Q. Okay. So traditional RAID requires the stripe units to be laid out in advance on the disk. That can take hours. And the controller requires the chunks of data to be written into the appropriate stripe units. All of this is often a performance bottleneck. The hot spares are idle during reconstruction, so we've got some wasted efficiency. And if you have, let's say you have RAID 6 and you have 3 disks failed, every bit of data on the array is lost. None of it is saved. So now we're going to compare Panasas RAID. An OSD is an object storage device. Each of the storage nodes that we talked about is also known as OSD when we're referring to it in its logical sense. The object-based RAID scrapes data across OSDs in a blade set instead of a predefined number of disk in an array. And we will talk about more of that later in this topic. And the RAID grouping for one object is not a whole bunch of data. It is one object itself. Each object gets its own RAID grouping and striping. That's the object-based RAID. Stripe layout for the object is created when the object itself is created. For files, the stripe layout of the file grows as the file grows. The parity is not calculated by a RAID controller. It is calculated by the direct flow client writing the file. It is written by that. So there is no performance bottleneck because the more clients you have writing, the more RAID engines you have writing. That is why we are scalable. The more we use, the higher performance that you get. Spare OSD space for reconstruction is provided as a distributed virtual spare space on each OSD in the blade set. So there are no idle OSDs in the blade set, no hot spares, and we'll talk about that later as well. If the RAID redundancy is exceeded by too many OSD failures, some individual objects may be lost. We may not be able to reconstruct those. However, a lot of the data can be reconstructed if that data is lucky enough not to be stored on, say, 3 failed OSDs. It all depends on the size of the blade set and the size of the files. A lot of times, a lot of the data can be reconstructed. I can't remember having to having a triple OSD failure and having to do this kind of recovery on ultra nodes. We have had to occasionally do it with storage blades way back, but should we need it, it's there. And we'll talk about that some on Friday. Okay, let's take our last break, and we'll come back at 10 past the hour.